Thank you for the introduction. I appreciate that very much, Carlos. And I would invite your attention to the title that's published. That's actually the title of the workshop that will follow in the Londra room immediately following this presentation. This landslide is the deadliest landslide in the United States history as a single event, killing 43 people and damaging an entire community. I'd like to acknowledge two things. First of all, the large group of co-authors whose names appear on the screen before you, without whom this would not have been a possible production. And also the association that is known as GEAR, that's Geotechnical Extreme Event Reconnaissance Association, which is supported financially by the National Science Foundation. This animation will give you a dramatic effect of what happened on the 22nd of March this year. The small community, Steelhead Haven community, was completely wiped out by a landslide that was a reactivation of a landslide that had moved previously in the year 2006. So that gives you a dramatic and impressive view of an extreme event. I will move to the next one here that is a different perspective, produced by newspapers. The first one was the New York Times. This one is the Seattle Times. This is a useful one for allowing me to point out a position right here on the image that will be important in the interpretation that will come in a few minutes. This is the location where a copy of the report may be downloaded at no cost. It's the geerassociation.org website. That's the image that will link to that report. We have a whole host of reports, mostly about geotechnical effects of earthquakes, but you're welcome to download any of the reports there at no cost, and hope that you do, actually. geerassociation.org. The setting is north of Seattle. Seattle is off of these diagrams below the stage level. This is a state highway, but not far to the west is Interstate Highway 5 that runs all the way from Mexico to Canada. These mountains are the Northern Cascade Range in northwest Washington. A valley that runs towards the west is the valley of the Snohomish River, and the Oso landslide occurred about in the middle of this image. There's a fine red box outlined on this diagram on the left, which is the depiction on the right that shows the outline of the slide that occurred this year. In red and white, and in yellow is the outline of the slide that occurred in 2006. The shading here is ground surface slope in degrees, and you can see gently sloping terrain for the most part, steepening with a steep edge at the top of a bench. The bench to the west of the landslide has a name, the Whitman Bench, and will have some significance in a few minutes. So the geology is listed here, or depicted here, from top to bottom, from the head of the landslide down to the floodplain of the Snohomish River, recessional outwash of sand and gravel, overlying till that was overridden by ice. In fact, it was the ice contact deposit. As the ice was advancing from the north, it created an advanced outwash deposit of fine sand, which also was overridden by ice. The ice at this location was about 1,200 meters thick, so very thick ice sheet. As that ice moved in the lowland first, it created an ice dam at the west end of the Snohomish River Valley, and it was in the reservoir of the ice dam that glaciolacustran deposits, primarily silt and clay, were deposited with a characteristic varved appearance and also overridden by ice, which gives it a physical property of overconsolidation that had a role to play in the characteristics of the landslide that occurred. And lots of landslides that are in this darker color, the darker yellow-brown color. So there's many landslides in this part of the valley. Shortly, within a week of the occurrence of the landslide, which is shown in red outline here, the U.S. Geological Survey by Dr. Hagerud developed a map that used LIDAR topography, and you see it here with color zones depicting 4 generations of landslides that were recognizable in the hillshade depiction. The largest one the most recently active are given letter designations A. There's just a few of them. The next older ones are given B designation, and one of them has a characteristic very similar to the characteristic of the Oso landslide this year, only a little larger scale. I would point out in this depiction a lobe of landslide deposit that is connected to this landslide here, and it looks like that may have been a similar flow-type movement that emerged onto the floodplain more distance than many of the other landslides. LIDAR was invented or developed in the Puget Sound area in 1999, I believe. And so we've got excellent resources available to us at this location. On the left, you see the LIDAR data from the year 2003 and the condition of the slope right here where the Stillaguamish River is flowing in this direction and impinging on the slope to create the instability. It's the engine of instability. 2013, 10 years later, another mission of LIDAR was acquired. The landslide of 2006 shows up very clearly with an adjustment in the channel. At this location, in this magenta color, is a log revetment that was put in place in the year 2007, primarily to stabilize the landslide because of the silt that was entering the river and affecting the quality of the fishery resource. So that 2013 is now on the left, an image that was flown within a week following the occurrence of the landslide is shown here, so you can see the characteristics very clearly. The yellow outline is the boundary of the 2006 landslide. Simple subtraction using the LIDAR digital resource. The red is negative result, and the green is positive. The green up here is actually turbid water that was impounded by the landslide dam. In 1952, a consulting report was done for the State Department of Natural Resources, again because of the fishery impact, and some interesting names were given to features here like Slide Creek. A mud flow occurred in December of the year during the field investigation, and so this stream is called Mud Flow Creek. Major spring, 850 liters per minute discharge, nearly constant discharge, was flowing in a stream that came close to the main scarp of the landslide or the lateral flank, and so this stream is called Headache Creek. Very romantic. And in addition, another feature that we heard a little bit about yesterday was the removal of trees. Scott Burns' presentation mentioned that. An area that was being logged between September and December 1951 at that location at that time. So lots to work with here. These features that are mapped out here are observations that were made by the team of geologists and engineers supported by gear, those of us who are listed on the front cover. I will not go through any of them in detail, but I will point out that we benefited from the University of Washington having a radiocarbon laboratory, and two of the individuals, by the way, Joe Wortman is at the meeting, at the conference here.
I don't know if he's in the room, but Dave Montgomery, also a geomorphologist on the faculty at the University of Washington, had access to that lab and collected samples that were dated to demonstrate that the pre-existing ancient landslide had a calendar-corrected age of about 6,000 years. So that's a very helpful piece of information that we rarely have. We mapped this into zones based on features that were observable. The mission of GEAR is to capture perishable data, data that will be washed away or somehow overgrown and no longer available for observation and documentation, and we try to do that quickly. So based on those observations, we identified a number of zones. We're calling them A through F. I won't go through them in all details, but but the area of the upper part of the bench that has a lot of mature trees on it is right here. We're calling that zone A2, and some rotated materials down here. The sheared glacial-lacustrine sediments are exposed in zone D. Zone E has different kind of trees, different degree of maturity of the trees. We believe that is the surface of the ground from the 2006 landslide, and it was the first part to move as a block, and the front part of that liquefied and ran across the floodplain as a debris flow. So probably debris avalanche, debris flow, and then these were more traditional landslide movements with rotational components to them. You've all heard of earthquakes. Well, these are slide quakes. The vibrations generated by the movement at the Oso landslide were recorded by a number of the stations in the Pacific Northwest Seismograph Network. The largest pulse occurred at 10:37 local time on Saturday, the 22nd of March. It was followed approximately 4 minutes later by another pulse and numerous smaller pulses that continued to occur for a matter of hours. Joe, with the resources he had available, used the seismic record to calculate the velocity time history, which you see here as absolute value, so that it's easier to visualize the area under the curve, which is an expression of the amount of energy released. With knowledge of the seismic records, the slide quakes, it appeared that two major pulses of movement occurred. With our observations based on the surface features, we divided this into stage 2, which is the more coherent, traditional appearing rotational block type movement, and stage 1 rather, being the debris avalanche and the debris flow. Whoops, I'm sorry. I would also like to point out that we have clear indication of liquefaction and ejecta that look exactly like what we see in earthquake-induced liquefaction phenomenon. No earthquakes occurred to be even remotely considered as a possible contributor to the triggering of this landslide. I want to show you some details here. This is a high-resolution photo taken 2 days after the landslide occurred by the State Department of Transportation. We'll start up here at the top, where you can see a collapse of material from the main scarp overriding trees in zone A2, and this is our zone A1. So there's clear stratigraphy here to be seen. This is the area that I pointed out in the oblique photo. And you can see material, which is the glacial-lacustrine sediments that are running up onto and burying trees, so that this zone E must have come to rest before the collapse and movement of our zone D material. You can see in this location the scarps, the internal scarps, and some interesting qualities. Notably, right here where the pointer is aimed is the scratch mark of this tree that was dragged across the landscape during the extension of the landslide movement. All of the canopies of the trees in this part of the landslide are towards the north, northwest, indicating a monodirection. It's very clear. The highway is at the indication of this bluish line. The yellow square marks an area of material within the debris flow. It turns out, that this part of the highway was an elevated ramp that had guardrail. And so what is shown here in this photo is asphalt pavement that is concealed or covered by, really, debris flow type material, and underneath this is a challenging advancer to use. So this is the asphalt pavement, and underneath it is the base material as part of the pavement section that was moved as a chunk by the landslide and debris flow. This is a vector map of several different sources of information. We know that the rescue crews were getting specific information. Sadly and tragically, it came almost exclusively from human remains, and they were very guarded about giving that information to us. What they did agree to give us was general boundaries, which are shown here in black and white lines, that would be an indication of where some actual residences were located and where the remains were found. So you can see trajectories that validate what would be logically considered, but nonetheless we're seeking actual data, and this is the best we can do from that source. The magenta line is the log revetment. We found clear pieces of that revetment at these locations and down here. Much of the rescue work, all of the remains that were found, by the way, were found in the debris flow zone. Meaning that the landslide raced across the floodplain, wiping out everything in its path in the first few, I'll say, seconds. It might have lasted a minute, very rapidly. And so that's where all of many of the houses and cars and all of the surface features that were obliterated were moved in that direction. I won't say any more about that. I'm hung up again. So what magic did you do here? There. Okay, I want to go back. So I won't take too much time here, but anecdotally, this was considered to be the wettest spring on record in Seattle, and it really wasn't. It depends on what gauge was being used. Some individuals at the University of Washington did a statistical analysis with an interesting hypothesis. They wanted to go backwards in time, and that's marked here by days, from the date of the landslide. And so you can see 3, 7, 10, 14, 21, all the way up to a full year of days. And there's two types of information here. Cumulative precipitation in millimeters is shown here on this continuous smooth line, and return period in years is shown in the more jagged red line. So you can see up to about 2 weeks before the landslide occurred, the precipitation was in the 10 to 15 year return period. 21 days, I think that's 21. It's hard for me to see at this angle. 21 it is. Was nearly the 100-year event, or the 100-year return period on the amount of precipitation that was accumulated over that 3-week period. and then it dropped down to below 40 year return period, and then much lower than that. So it was a really wet March and early and late February. And there's more on there that I won't take time to talk about here. The gray band across those that have gray bands represent the 30-year normal precipitation, with the upper line being the 75th percentile and the lower line being the 25th percentile. Highlighted in yellow, and the normal precipitation is a 30-year average. The yellow shows the fall of 2013 and the winter really, of 2014. So you can see that September was wet, but October, November, December, and January were not particularly wet. March was not wet at Arlington, down here at number 1. Everett at number 1. Arlington was above the 75th percentile. The concrete fish station, concrete for a dam that's located there, March was wet, and March was very wet at Darrington, which is the gauge that was used for the statistical analysis. So you can see there's variability here, and I want to focus in on some of that variability. This is about 1 hour of data from weather radar. It's a Doppler radar in the United States. That's a wonderful resource. The scenes you see here are approximately 5 minutes apart. And the colors are listed over here. I won't spend any effort to try to tell you what they mean in terms of instantaneous rain rate. That's what the Weather Service calls that. But the warmer colors are higher radar echoes and higher rate of rain, higher number of drops of water in a volume of air. The translation of this at the Oso landslide, which is dead center on each of these diagrams, it's all the same area, by the way, amounts to about 0.376 inches in, or 9.6 millimeters per hour for the period that's shown here. So that's the value that this information has. This is now a week of information for a couple of the station's rain gauges, Marble Mountain, Gold Hill, Finney Creek, and then Darrington. This is the one where the statistics were done. The other point up here is Oso landslide, the head of it, and of course there's no gauge at that location. So I won't take much time to go through here, but I will invite your attention to the solid blue line, which is a more continuous line for Darrington. It comes across here to about 4 inches. We're using inches here. That's the units that are being recorded. The rain gauge for this 5-day period was a little bit higher than what I calculated from the radar data. So that's Darrington, about 15 or so kilometers to the east of Oso landslide. And here is Oso. The cumulative here is 9 inches. So it was 9 inches at Oso by the calculation that produced a little over 4 inches at Darrington. Substantial variability. The yellow and red double-headed arrows here mark a specific scene, which I will show you here. And you can see Oso has warm colors around it, meaning that it was raining heavily. Darrington has cool and green colors here, means that it was raining but not heavily. Gold Hill, Finney Creek, and Marble Mount are clear, so it was not raining at those gauges. That's a good snapshot of the variability of precipitation. Now we'll switch to stream gauge. This is January of 2012, January of 2013, January of 2014, going up to the end of March at a gauge that's located 13 miles. I can't remember what that is in kilometers. 15, I think that's probably 20 kilometers away. I've highlighted something here at discharge. This is 283 cubic meters per second discharge, just as an index to help us keep track of something, and that is excursions that exceeded that. There was one in February of 2012, one in January of 2013, one in December of 2013. I'm having trouble with the alignment here. I think this is January and this is March. There were 3 in March of this year. So that was the heavy rain period for 21 days in advance of the landslide. And if we zoom in, this is January, February, March of this year. The landslide occurred on the red bar. There was some ice that obstructed the gauge at this location and an immediate drop. That's an anomalous drop associated with the landslide dam. And here you see more detail, the 19th, 20th, 21st, 22nd. That's 10:37 in the morning from the seismic information. That's when it occurred. This gauge is 21 kilometers downstream, and that amounts to 2 meters per second river flow. You can see an immediate abrupt drop and return to base flow, and then a really sharp increase that tapered off, that moderated and resumed a base flow condition. Another gauge is located 50 kilometers to the west under the influence of Puget Sound and sea level tides, and so these high peaks are high tides. 1037 occurred at this moment on this graph, and the influence of the landslide dam is visible right here, again amounting to 2 meters per second river flow. The run out, I think there is some discussion. I've heard some discussion about this. We used the information that was available for the total volume, as well as splitting the volume into either an 80% or a 50%, not knowing exactly how much the stage 1 volume was. That's the one that did all the damage. And the Farböschung geometry is shown up here from the crest to the toe, the crest of the landslide morphology down to the toe of the runout. And so these points plot in here under, the non-volcanic and volcanic trend line. A little bit different depiction over here, different database, and depending on whether we calculate it with the simple way or a different way described by a, with the statistics now, the 6,000 year over the distance that we had, some information. This is the USGS landslide mapping. We're looking at a range of recurrence of landslides, depending on how it's calculated, between 400 years and 1,500 years. If we look at 15 landslides over that distance and an age of 6,000 years, that would calculate to 400 years between large landslides if they're all independent of each other in time. If they occur as generations of landslides, some landslide weather, so to speak, or maybe even some of them are earthquake-induced. Clearly, the Oso landslide was not. But that would be 4 zones over 6,000 years, which would give us an age of about 1,500 years per generation. So something about risk. I won't take time to go over that, although it's important. And in conclusion, as a final thought then, although it was thought that this was the wettest spring on record, certainly it was the wettest March at the Darrington gauge, that we can say. The fall and winter were about normal. It turns out that the Oso landslide was the only landslide, the only major landslide that occurred in northwest Washington this year. So if it's a really wet year, you would really expect to have many landslides, and we had only one, and it was a deadly one. So the bottom line is that this was not a big year for landslides in northwest Washington. It was a year of a big landslide. And with that, I thank you very much for your attention and invite you to go to the Extreme Event Workshop in the Londra room immediately.